Okay, the next talk is by Jacob Forshaw. So Jacob is finishing up his PhD at the University of Calgary. And before that, he obtained his bachelor and master degrees at the University of Oxford in the UK. He has already a quite broad spectrum of research interest for such an early career scientist. And I'm just going to list a few of them. So for example, assessing the role of kinetic impediments to reaction during regional metamorphism, especially for pelitic rocks. As part of this is also studying the fundamental processes that dictate the formation of rock microstructure and texture. And I would say personally, as one of the great contributions of Jacob to come is the compilation of natural databases in a number of rock types from different tectonic settings in order to test, but also maybe in the future to develop new thermodynamic models. And I think that, Jacob, this is exactly what you are going to talk about. And I'm very excited to see how good or bad are the models in reproducing the natural patterns. So please, Jacob, the stage is yours.
Great, thanks very much, Pierre, for that lovely introduction. Just let me share my screen, everybody. Okay. There we go. I assume that's all good. Excellent, thanks, Pierre. Okay, so this is the final long format talk of the workshop. And I'm going to be talking about the assessment of these thermodynamic data sets and solution models against the natural record. And because this is the final talk before our shorter discussions tomorrow, I wanted to kind of start with this question because it sets up my presentation quite nicely. And that is to say, what are we doing? Why are we doing phase equilibrium modeling? And the answer is that the majority of us are attempting to reproduce nature and obtain some kind of pressure temperature estimate. And that's why we're all here at this workshop. I put this phase diagram on the right-hand side here with pressure and temperature, and we're trying to get at this red star. What were our PT conditions for our rock, and what does that mean for the tectonics of the region in the past that we can imply from that? And therefore, I would argue that natural samples provide the ultimate test for how well our thermodynamic data sets and solution models are performing. At the end of the day, if models don't reproduce natural observations, then there's a problem. And so if that's the case, you have to ask yourself, well, why do models not reproduce natural observations? Now, we've had a great talk yesterday from Pierre considering reactive bulk composition. And this is one reason why model might not equal nature. You might have not considered appropriately which minerals are in equilibrium with each other when you're forming your bulk composition to use in your model. And we've just heard Dave Patterson talk about these kinetic factors, and that these may lead to overstepping of reactions and differences in the in what we observe in the assemblages, perhaps. And I will say that these two kind of overlap in that they're disequilibrium features. And so there may be the reason that your natural observations in the rock don't match the model because there's some disequilibrium taking place. But there's another issue that we often perhaps don't think about, and that's that there are problems or issues with the thermodynamic data sets and the solution models themselves that we're using for calculations. And I've put that in this red box here. So I want to ask, can natural data be used to assess the reliability of these data sets and solution models? Can we use natural data to get at the red box? I'm going to say that, of course, in natural data, there may be some examples of disequilibrium, but can we see through that and consider just how well are the thermodynamic data sets and solution models that we have reproducing what we observe in nature? And so to kind of I don't know, up front, I will say that the success, as Dave said in his talk, of the metamorphic Feishi's principle, that we see these repeated patterns in mountain belts throughout the world, for me, that's evidence that the equilibrium model of metamorphism accounts for these broad features in a metamorphic sequence. And I put an example metamorphic Feishi's diagram down here. The kinetic factors, as Dave pointed out, become an issue when we start to move toward this idea that metamorphism is continually progressive and that a rock on its prograde path continually equilibrates. And that's not what I'm talking about. I'm just looking at the peak assemblages as part of this talk here today and making my comparisons. There's one other issue with natural data that makes it hard to make this comparison, and that's that unlike the equivalent experimental data, we didn't set the pressure, the temperature, the oxygen fugacity, or any other parameters. Nature set those for us. And so how do we make a comparison between natural rocks for which we don't perhaps know the PT conditions and what we observe in the model? But there's some hope here. And I've put up a map of barrow zones here with some representative outcrop pictures, not from barrow zones, I should note. But if we go in the field and find a store-like garnet biotite bearing schist, like this one in the center, and then we see similar rocks with mineral assemblages, perhaps along this band. And when we move north, we see the loss of staurolite, and we only have sillimanite garnet biotite in another band. And further south, we see biotite in a band again. You start to realize that actually we have relative pressure temperature constraints, in that we know the sillimanite rock, because of the relations, has to lie at higher metamorphic grade than the staurolite rock and higher than the biotite rock. So it's not all hope isn't lost. We have relative constraints in the pressure temperature conditions. And we can start to look not only at the mineral assemblages in these sequences, but also the modal abundances and the compositions and how they compare. And the beauty is that, as I said previously, this same sequence and many other sequences, they're found worldwide. I've put some examples up here, one from the Canadian Cordillera, another from, this is Dutchess County in New England, Colombia here, barrow zones, and then the Damba culmination in Tibet. And so we find these same sequences, and therefore we can find the same assemblages and modes and compositions that we can compare between them. So have I answered this question? Can we use natural data in this assessment? Well, in my opinion, yes. Rocks typically approach equilibrium at peak pressure temperature conditions. And the sequences of rock provide these relative PT conditions that we can use to test the models. So how do we use natural data in this assessment? Well, the answer is that we need to compile databases of natural data from the literature. We need to compile all of these different sequences that I showed in that previous slide, so that we can identify what are the repeated, consistent, and systematic patterns in either mineral assemblages, mineral abundances, or compositions. And that's what I'm going to talk about today. So the majority of my work for the last few years has focused on metapolitic rocks. And this is built on Dave's work of the last 30 years or so. And we've been building these databases. The first is of a 2,500 whole rock analyses in metapelites. The second looking at, and this is the bread and the main part of the databases. This is the 100 prograde mineral assemblage sequences. So example, I gave you the Barroso sequence, 100 of those from different areas around the world with 1,500 samples with complete mineral assemblages, 5,000 EPMA probe mineral compositions, and then a kind of subsidiary database that I'll get to at the end that looks specifically at 500 samples with 750 iron 3 analyses in individual minerals. And that's because obviously the probe can't get at iron 3 plus in lots of minerals. So I'll focus on this whole rock analysis database first. And I'll bring back up this same slide, but with a new question. And the question is, are all metapelites equal? If I'm going to make a comparison of the rocks, the assemblages, the compositions, the modes across this sequence here, and then make a comparison of that with whatever happens in New England, I need to make sure that I'm broadly comparing something of similar composition. And that's why we wanted to look at the bulk compositional variation that exists in metapelites throughout the world. So I pulled out 3,323 whole rock analyses from the literature. And obviously, when you're doing this, some anomalies end up slipping through the net, I suppose. And so I removed any calcareous rocks to keep it just at non-calcareous metapolitic rocks. So anything here that was above 4 weight percent CaO, and the x-axis here is XMG. It's not that important actually, but we just focus on the y-axis. I also removed anything that would be considered a meta-arkose or a meta-aronite or a quartzite, these kind of low aluminium rocks that have less than 12 weight percent Al2O3, as I've defined it here. And then I separated out my meta gray wackies from my meta P-lights. And so the axis here on the left-hand side is XK, as I've called it, which is the potassium over the potassium plus the sodium. And I've used a value of 0.4 here, which in mole percent relates to 0.5 in weight percent. So anything that has more sodium than potassium, I've classed as a gray wacky and removed. And this leaves me with 2,469 meta P-lights that I can use to look at, well, how varied is our politic composition. And typically in metapolitic rocks, we use AFM diagrams after Thomson, and I'm showing Frank Spear's one here from his big blue book with his fields for different high aluminium P-lights and low aluminium P-lights. And I wanted to look at what's the distribution of these 2,500 rocks, you know, with relationship to the garnet chlorite join, with relationship to XMG. And so that's what I'm showing in this plot here. Now, this is a little bit different to the AFM diagram, and you can think of it that I've simply opened up the A-axis. So I've not divided for my Y by AL203 minus 3K20. I think this is the same as if you scroll in Thomson's 1957 paper, it's figure 8 of his paper. And the beauty of this is that then all of these samples have an equal XMG value. It's not affected by the ternary. And we can look at the spread of these 2,500 rocks in AFM space. And so you'll see that actually the majority of them concentrate around here and they spread across this garnet chlorite join. There's no, you know, bias towards high or low P-lights, I don't think here. And I'll tell you that 65% of them sit within this red oval that I'm plotting here. So the point of this is to say that whilst there is definitively some variation in the composition of these meta P-lights, we see variations in the XMG, higher iron ones, lower magnesium ones, and variation in the aluminium. The majority of them, I would argue, lie within a relatively restricted compositional range. And so making these comparisons between mineral assemblages and compositions is fine to do upgrade. I've also put an average here, this star, that represents the average of the 2,500 metapolitic rocks here. And that's what I'll be using in all my phase diagrams when I get to that in a little bit. And I've also put the averages of some other really prominent studies that looked at the compositional variation in P-lights. So Shaw's 1956, Ague 1991, and Atherton and Brotherton 1982. And you can see these generally fit in about the same area. So we're getting a similar answer. One thing that this diagram, before I move on to my assemblages, this diagram doesn't show that I'd like to highlight here that I think is really underappreciated of when people are studying metapolitic rocks, is the importance of iron 3+ in meta P-lights. When you go and read Shaw and Ague and you look at the values for XFE3+, XFE3+ here I've defined as the iron 3+ over the total iron in the rock, they get 0.28, 0.25, 28, 25% here. These are in their high grade and amphibolite Feishi rocks. And this is, most people often model when they do their phase equilibrium modeling without considering iron 3+ in meta P-lights. It's not the case always, but some people do. And so I decided to go and take the 1,277 of my total P-lights that had a separate iron 2, iron 3 determined and plot them on this diagram. This shows 0 to 1 XFE3+ here, and along the bottom is XMG. Apart from now, I've removed the iron 3+ component, so it's just magnesium over magnesium plus iron 2+. And I've colored them according to the density as to where the majority of the analyses sit. And you'll see that there's quite a large spread from 0 to 1 on the iron 3+. But in general, what I've done here is I've put a dashed line and I've culled anything that had above 0.4, as these are probably really unusually oxidized red beds or something. And I've looked at all of the slightly less oxidized rocks down here, and the average from these 1,056 that sit below this line, XFE3+ is 0.2. So there's quite a reasonable amount of iron 3+ in our meta P-lights, and that's important. And I'm going to come back to that point perhaps tomorrow and later on in the talk. So I hope I've convinced you that it's somewhat appropriate to make these comparisons in mineral assemblages and compositions of grade. So let's get on to the meat of this talk, and that's the database of 100 prograde mineral assemblage sequences. And to do this, I'm going to introduce what I'll call the Feishi series. This is named after Miyashiro, 1961, Heighton in 1965. And the Feishi series really just means sequences of mineral assemblages. We all know that metapolitic mineral assemblages are sensitive to temperature. They develop different porphyroblasts as we go upgrade here in barrow zones, but they're also quite sensitive to changes in pressure. And a caveat here is that I will be focusing on the sequence or the order in which these isograds appear. I'm not going to be looking at the spacing, which may reflect different thermal gradients or even kinetic effects, as Dave Patterson pointed out, and may change within even within an area. Look at this map of barrow zones here, and the width of the zones kind of pinches and swells in places. So I'm just looking at the sequences in order because these are very repeatable in different mountain belts throughout the world. Okay, so what I'm going to focus on will be quite a broad area of PT space, the amphibolite facies into the granulite facies, probably 400 up to 750, 800 degrees C, and a wide range of pressures here. And this is where the metabasites that kind of define the metamorphic facies don't show a lot of change. We'll talk about that later. But the metapelites have these very sensitive, they're very sensitive to the changes in pressure and temperature. So the right-hand side diagram is a schematic diagram that shows the PT fields for critical mineral assemblages for an average bulk composition. Obviously, these fields move if you play with the aluminium or the iron or the magnesium, etc. But we're just looking at that average P-light that I talked about earlier. And there's an assumed, I suppose, spacing between these because we know where quite well from experimental results where the chlorite out, the muscovite out boundaries are and the aluminosilicate triple points, but just focus really on what mineral assemblages are present there. And I'm going to show you how we get this diagram. And we get this diagram essentially because we go and look at isograd sequences in the field. So on the left-hand side here, this is an isograd map of the Etive Oriole up in Scotland. And you can see that as we move from Loch Orr north towards the quartz diorite intrusion, we go through a number of isograds, and we can map and not the spacing here, remember, just the order in which these isograds occur. So we go through cordierite in from the biotite zone. We then have K feldspar in, followed by andalusite in. And then I'm going to skip a couple of isograds on this map because they're not in typical metapolitic rocks. We then see melting as migmatites occur, and then finally sillimanite. So that gives you the order, and I've placed that same order on the diagram on the right-hand side. Okay, let's go to another example. This is the Onawa Pluton and its associated contact Oriole in Maine. And you'll see here that as we go towards the intrusion, we go through cordierite in, andalusite in, K feldspar in, sillimanite in, and then migmatite in. Now, this is really interesting because you'll see that compared to the previous Oriole that I showed you, the sillimanite and migmatite isograds have switched. So that tells us something about the slopes of these reactions and where they perhaps occur. Here's another example here. This is what we call a Feishi series 2A. I'll get to the names of these at the end. Don't worry if that's confusing you for the minute. This is the Bugaboo batholith in the Canadian Cordillera, and we're moving towards it as we go in this direction north here. We have cordierite and andalusite come in at this boundary, followed by sillimanite in, which is labeled by fibrolites here, and then K feldspar followed by migmatite. So, you know, the interesting thing about this is that we've switched the order that sillimanite now comes in before K feldspar. That's a really good constraint, and that's because these two reactions have different slopes. The andalusite to sillimanite reaction is negative, and the muscovite out reaction has a positive slope. Okay, here's the example that Dave gave earlier in the Nelson Oriole when he just gave his talk this morning. We can look at the isograds here: garnet in, staurolite in, and andalusite in, and then sillimanite in, followed by K feldspar in at higher grades. Here's that example I showed earlier from the Canadian Cordillera once again. Kind of Canadian-centric here, I realized that that's a little bit of bias there, perhaps. There are many of these worldwide. But we see garnet come in, followed by staurolite and kyanite, and then sillimanite. And so the point of me showing these examples is that we've just taken the order of the isograds as we see in nature and produced this schematic diagram on the right-hand side. And actually, it's more complicated than the 5 examples I've shown you. There are maybe 10 Feishi series, as we call them, and I've labeled them on the right-hand side here. So we go from 1A up pressure all the way to 6. And we see these, the point is that not only in these 1 isograd sequences that I've shown as an example for each, but there are multiple of each example. And so these numbers on the left-hand side are the number of localities where we observe that same sequence. 6 1As, 13 1Bs, 23 1Cs, 25 2As. Only 3 of this 2A prime sequence. This is where you only observe andalusite and no staurolite or cordiorite. These are quite rare. 31 2Bs, 3 3s, that's the staurolite sillimanite sequence that Dave talked about this morning. And then I've put numbers against up here, 29 and 2 for these Barovian type staurolite kyanite sequences, but they're just the numbers that I have in the database. There are many Barovian sequences worldwide. And so the point of me taking the time to show you this, despite it not being quite phase equilibrium modeling, I promise I'm going to get there, is that I hope I convince you that there are these very, very repeatable, consistent, and systematic patterns in the mineral assemblages that we can use to assess the models. And I should note here again that this isn't something that's new. This is the numbers here are based on Patterson and Tracy's 1991 paper where they define the Feishi series in lower pressure contact aureoles. And as I said earlier, the concept is, based on the Batha zones of Carmichael and the Feishi series of Heitinen and Miyashiro. Okay, so now let's get in. We're here to do phase equilibrium modeling, right? So everybody wants to know, well, how well are these assemblage patterns that you see in nature reproduced by the modeling? And firstly, I've got to have this kind of long slide here where I tell you, what have I been using to do my modeling? Well, I wanted to test the different data sets and the solution models against each other. And so I've done 4 sets of modeling highlighted by these 4 boxes here. The first 3 all take advantage of Holland and Powell 1998 dataset 5.5. And I've denoted these HP1, HP2, and HPT. And you'll see that on the right-hand side, these all use the same AX models, or solution models rather, for chlorite, cordiorite, muscovite, melt, etc., etc. The difference between the 3 is that they use the same data set, but different solution models for biotite, garnet, and ilmenite. So HP1 is a slightly earlier, it uses earlier models, White's 2005 model, Tinkham's 2001 garnet model, and then an ideal ilmenite model. HP2 uses, and I believe this is the same as TC330 as when that was released. It's White 2007 biotite, garnet is White 2007, and ilmenite is White 2005. The difference here is that garnet and ilmenite now have an iron 3+ N member. And then I've used HPT, and really I think of this as the exact same as HP2. I've just switched the biotite model for Lucy Tachmanova's 2009 model. And then I'm going to compare the 3 of these to dataset 62, which has a kind of rigid, strict set of solution models defined by Dick White in 2014 and others. And yeah, I will leave it at that. And if you need more information, please refer back to this slide in the notes. All of the modeling has been done in the same chemical system. I'm going to show some examples tomorrow of the effect of chemical system on these types of diagrams, but for the minute, it's all full system MN-NCKF-MASH-TOW. So how does nature compare to the model? Well, the diagram on the left-hand side is the exact same as I showed you earlier from the Feishi series. I've just colored it. I've made the staurolite field yellow, the cordiorite field blue. I've put the garnet inline in red. That obviously moves depending on the manganese content of your rock. And I've made the above the solidus, the melt bearing field hashed. And I'll put these up. These are the predictions of the models. So in the top left, you'll see I have HP1. In the top right, HP2. The bottom left is HPT, and the bottom right is dataset 62. These will always be in the same order on each of my slides. And we can look at how, even when I'm using the same average politic bulk composition, the choice of dataset and solution model has quite a big difference on the assemblage stability fields. So let's look in the top left here. This predicts a cordiorite field where the cordiorite and andalusite field here has a positive slope. That's different to what we observe in the field where it's actually a negative slope from what we can tell. We can compare that with HP2. We then see quite a large andalusite only field here, that 2A prime sequence. But we get a negative field in the cordiorite andalusite relation. So that's a pro of that model. simply switching the biotype model from White 2007 in the top right to Tachmanova 2009, we see that there's a 2 kilobar difference in where cordierite appears just by changing the biotype model. We still get the nice negative slope and perhaps a slightly wider andesite field, but that's a difference. And we compare that to dataset 6.2, and you'll see that cordierite only appears here once muscovite has left the assemblage. So kind of above this reaction here in my natural Feishi series diagram. And it doesn't predict any cordierite when muscovite's present, and that's not in accordance with what we observe in nature. Another really interesting point to look at is just look at the size of the staurolite field. Here it's, 4 to maybe 8 kilobars and 50 to 75 degrees C wide, and it increases as we go through or to newer and newer models and data sets, to the point in dataset 6.2 where it's 3 kilobars to 10 kilobars and 150 almost degrees C wide. And you can also look at the Garnet in isograd, and this is similar to what Dave Waters showed in his talk yesterday. In that, and I say isograd here, I mean Garnet in line. It varies drastically between data sets. So actually between HP1 and dataset 62, it's quite similar. But between HP2 and HPT and the others, it's a much more restricted Garnet stability. Okay, so that's just an example of the differences these make. I'm coming back to this slide again now to say, let's now have a look at the compositions. We've established these repeated consistent patterns, but I said that not only did we pull together all the authors' complete mineral assemblages, but if they analyzed mineral compositions, we pulled those out of the literature as well to make these databases. So how well are the compositional patterns reproduced by the modeling? And the first point I'm going to make here is about compositional patterns in pressure temperature space, or in pressure temperature. And we'll come back to this Feishi series diagram on the right-hand side, and I'm going to make a simplification. So on the left-hand side, I've put up what I'll call a gridded version of the Feishi series of this diagram. And to explain what I've done here, I'll highlight an example. This orange box highlights Feishi series 1C. And you can see that as we go upgrade in these boxes, we go from biotite to cordierite andalusite. Well, that's the same here. This is the biotite zone, cordierite andalusite. And so I've just stacked the zones in order of increasing temperature for Feishi series 1C. And I've done that for every single Feishi series. Now, obviously, there's a slight issue with that in that we know that these different zones have different widths at different places. And so that may affect what we're doing, but it's broadly a simplification that you'll see increasing zones this way. And that obviously I've then stacked them all neatly on top of each other, all of these Feishi series, and perhaps the one zone isn't equivalent to the zone below it. But and there's one other issue, is that with the, or not issue, or the caveat, is that with the Feishi series, you'll see for 2B and up, these are not isobaric because they often occur in regional metamorphic terrains. So there's a change in pressure with the change in temperature upgrade. But for simplicity here, I've just put them as kind of isobaric. So there were a few kind of simplifications with this, but the broad point is that in the top left, you're at higher pressures and lower temperatures. And in the bottom right, you're at higher temperatures, lower pressures. And that's all you need to take away from this slide. What I am then able to do is I can go and say, right, well, let's go to the biotite zone of Feishi series 1C. And I will take every single biotite analysis that exists in the database, and I will average them to see what the average biotite composition is in that zone. And this varies from mineral to mineral, but there can be anywhere from 5 to 50 analyses in each of these boxes. And that's what I'm showing here. This is the compositional change in biotype with pressure and temperature. So we can focus on the left-hand diagram. The white boxes are where I don't have any data for biotites, and the colored boxes are where I've taken an average of the number of silicon cations of all the biotites from all worldwide in that zone. And I put a scale bar on the right. So you'll see why this scale bar doesn't quite match up here in a minute, but you'll see that we go from, there's perhaps more yellow khaki colors in the top left, and we move down to perhaps darker green colors in the bottom right at higher temperature, lower pressure. And we go from anywhere about 2.75 to 2.65. That's the variation we see in biotite silicon cations. I can do the same for any mineral and any cation. And here I've shown an example of biotite titanium cations. We've known for a long time that the titanium content of biotite increases with temperature. And so we see these kind of pink values at higher temperature here compared to the blue and green values that we observe at lower temperature. Again, white is where I've not been able to observe anything. So I hope that I can mention, the power of these databases is phenomenal for us to be able to look at how biotite silicon compositions vary, not only with temperature, but also with pressure. So on the right-hand side here is my same order of mineral, same order of solution models. And I've just plotted a pixel map using Domino and colored it to show the change in silica cations in each of the models. So you'll see that in the top left diagram, we go from 3 silicon cations at low temperatures, high pressures, to a low of perhaps 2.4, 2.5 silicon cations here at the muscovite out reaction. Remember that you can't directly compare the top left of this diagram with the top left of this diagram because this sequence isn't isobaric. In fact, this top point here probably represents 5, 6 kilobars and 450 degrees C. And so it might not, we don't need to reach these pink values is what I'm trying to say here. But the bigger take home is that in all of these examples, whilst there are subtle variations, silicon goes down to 2.3, 2.4 cations in biotite, and we never ever see values that low in the natural database. Here's a comparison for titanium cations. Now again, another caveat here, these top fields are usually migmatite in my classification. And I've not looked at compositions above the solidus because for reasons Dave Patterson will allude to tomorrow, that's inappropriate. I would have to have made another diagram and saturate the solidus. So when you kind of ignore or blur out those pink values, we go from blue to green here. And perhaps that's what we see nicely here in dataset 6, where we're getting up to green values, and the same in the Tachman over model, but perhaps not as higher values here in the top 2 HP1 and HP2 examples. And so, as I said before, this is possible for any mineral. This is the compositional change in muscovite with pressure and temperature. The left-hand diagram shows silicon cations. We know that the number of silica cations in muscovite is sensitive to pressure because many people go and use a Fengite barometer. And we broadly see that there are perhaps darker green values up here at higher pressures and bluer values at higher temperatures and lower pressures. There's this kind of odd green patch here at low pressures, low temperatures. I don't quite know why that's there. I haven't analyzed the data long enough for that. But there's some change here in the number of silica cations in muscovite. Although it is slight, it goes from perhaps 3.1 to 3.2 at the max. And we can look at the number of sodium cations in muscovite, the paragonite content. There's some slight variation here, maybe 0 to 0.1 at this high point here in the Feishi series 3. But generally, it's quite low. The majority of muscovite, the A site there will be made up of potassium. And we can compare once again with the models, right-hand side, the same order as I've shown all the way throughout. We get these high orange values here in the top left, but remember, as I said last time, that's not quite comparable with what we get. This box is probably 5 or 6 kilobars, and well, that's green and that's green, so perhaps it's getting close to what we observe in nature. And you see that there's a less of a variation in the silicon content of muscovite compared with biotite. Perhaps that's closer to what we observe in nature. Here's the sodium cations. On the right-hand side, you'll see that there's a max sodium number of sodium cations of around about 0.4 in all of the models that we see. It's perhaps worst here in HP2 of 0.4, 0.5 sodium cations, and yet we never see more than 0.1 in the natural data. Okay, there's one other thing, well, actually there's 2 more things. The first of which is we could also look at compositional patterns between minerals. Not only can we look at a single mineral and how it changes in pressure temperature space, but we can also consider, well, if I have 2 minerals in an assemblage, what is the distribution coefficient, or what is the distribution of elements between them? And that's what I've done in these diagrams here. These are KD diagrams. The x-axis is the XMG value of biotite measured in all these authors' studies that I've collated. And the y-axis changes from diagram to diagram. So A is biotite cordierite, so it's cordierite on the y-axis. B is chlorite, C is staurolite, and then D is garnet. And so these produce what I think know as the observations we see in nature. Cordierite is more magnesium than biotite. Chlorite is similar, perhaps more magnesium. There's a few outliers here. Perhaps these are retrograde chlorites that have been accidentally included. Staurolite versus biotite. Staurolite is more iron-rich than the biotite, and garnet is even more iron-rich than that. So we can look at the variation between these minerals. And as an example of that, I'm just going to look at the simplest one, I think, which is the biotite cordierite relation. This shows a really nice pattern here. And once again, I've gone and used the pixel map domino approach in Domino. I gridded it for 100 by 100, the same as I did when I produced those nice diagrams I had earlier on. And I just pulled out all the cordierite and biotite compositions in the blue zone of each of these diagrams. And then what I've done here is I've reproduced that same cordierite biotite diagram from before, and that's the same in A, B, C, D. And now I've replaced it with, over the top, the black dots represent the prediction from this previous slide by the models. So we can look at, HP1 in the top left. The black dots, well, they lie along this average natural line that I've included here that shows the average KD value between these. And you'll see here that there's a pretty good match. We go to dataset 55 HP2 and HPT, and the values have shifted left a bit. They're more iron-rich, the biotites. And we can compare that with dataset 62, and well, now they don't lie on top of our observed. They're actually really quite iron-rich, the biotite, in comparison to the cordierite. The biotites are more iron-rich in comparison to the biotites from the other data sets, the predictions. Okay, so one final thing on compositions, and that's this final database here of 500 samples with iron 3+ analyses, 750 iron 3+ analyses. And the reason this is kind of a subsidiary and separate database is that iron 3+ is quite important in metapolitic minerals, and yet if I show you an example EPMA analysis of a biotite from the database here, this number is iron total. It's total iron as FeO. I don't know what proportion of that is Fe3+ or what proportion of it is iron 3+, is iron 2+ rather. And whilst there are ways of estimating iron 3+ by charge balancing, this exists in minerals for garnet and pyroxene and oxides, where they're relatively stoichiometric with a definitive number of oxygens. You can't estimate it for iron 3+ in biotite, chlorite, muscovite, and staurolite. And so this database, the idea here was to pull all of the data that exists in the literature for examination of iron 3+ contents in these minerals in metapolitic rocks. And we ended up with this table here, biotite, muscovite, chlorite, staurolite. You can see there's relatively more biotite analyses compared to muscovite and chlorite and staurolite. And I've written the average XFE3+ of all of these values and the average number of iron 3+ cations for a certain number of oxygens per formula unit on the right-hand side. It's about 10% in a biotite, the XFE3+. It's greater than 50% in muscovite. Now, there's not a lot of iron in muscovite total, but if 50% of it or more is iron 3+, that's a significant component. It's less than 10% in chlorite and staurolite. The standard deviations on these are pretty big, and I think that actually shows that there's a wide range of iron 3+ in nature. And so perhaps these estimates, the estimates aren't, super well constrained, I would say. Okay, let's just take an example of one of these. And I'm going to talk a little bit about this tomorrow when I talk about handling iron 3+. Biotite here, the left-hand side, I've reproduced the average number of iron 3+ cations. It's about 0.14 plus or minus 0.09 for an 11 oxygens per formula unit. And on the right-hand side, I've plotted once again my 3 different models, and I've shown you how many iron 3+ cations these include in the biotite. So the top 2 models, well, they're pretty low. They're down here at less than 0.05 cations of biotite. Whereas the Tachmanova model and the latest dataset 62 model, these include much more, and they're closer to what we observe. This is the the standard deviation, the average and the standard deviation plotted against the scale bar here, and it's within error of what we see. There are more in-depth calculations I've done on this, but I've spent enough time talking about it, and so I think I'll move on. I'm happy to answer questions about that later. Okay, so let's take a break there for a second, actually. I've talked a lot about the metapelites, and they're not the only rock type that we look at and are interested in. We use models for lots of other different rock types. And so for the final part of the presentation, I'd like to talk about the metabasites. And the reason this isn't a significant part is that this is more of an in-progress database. I have around about 800 samples ranging from green schist to amphibolite to granulite facies, many with modal abundances, 3,000 mineral compositions for amphibole, garnet, clinoperoxene, orthoperoxene, plagioclase, oxides in places. But it's not quite there yet. And so I'm just going to show you why we can do similar things that I've done in the P-lights with some very nice examples from individual areas rather than the entire database here. So there are mineral assemblage sequences in metabasites too. They're also sensitive to pressure and temperature, just perhaps much less so in terms of the assemblages that develop. And I'm going to focus here on the green schist amphibolite fascies transition for this slide. Here's two examples. The left-hand one is the Mount Menzies area, where the comets and volcanics have been metamorphosed by this contact aureole here in the north on Vancouver Island. And the right-hand area is Flin Flon in Canada, and that's in Manitoba. It's a regionally metamorphosed sequence, part of the Trans-Hudson orogen. And so if you go and look at Terabayashi's work here and what he mapped upgrade and what they mapped upgrade in the mineral assemblages, you'll see that oligoclase comes in before hornblende. So that's the order of the isograds as we would have it. You compare that to Flin Flon, where Paul Starr's work mapped that hornblende comes in before oligoclase. And so you'll see that there's a reversal in the order of the isograds here. And that's all to do with the slope of this epidote amphibolite facies field, actually. So the purple line represents the Mount Menzies area, which occurs at lower pressures, where oligoclase or epidote leaves the assemblage to form oligoclase before hornblende enters the assemblage. Whereas in Flin Flon, I've used the orange arrow to indicate increasing metamorphic grade, and that occurs at higher pressure, and it goes through the epidote amphibolite facies with hornblende before you introduce oligoclase. There are examples from higher temperatures as well. This is looking at the amphibolite granulite facies transition. The top diagram is a map from Percival's work in the Capus casing in Canada, Ontario. Again, very Canada-centric. That wasn't meant to be the way. And in the bottom is Broken Hill, Australia, from Bin's classic study in 1962. And if we go through the isograd sequence in Capus casing, we go from amphibolite, we introduce clinoperoxene without orthoperoxene, and that's key. And then we introduce garnet without orthoperoxene. We compare that to Broken Hill, where we introduce, we go from amphibolite to an amphibolite with a brown hornblende, as Binns describes it, plus or minus some clinoperoxene. And then we introduce orthoperoxene without garnet at higher grades. And so once again, we can use these sequences to say, well, we know garnet occurs at high pressure, and therefore the orange band here goes into the high pressure granulite area, whereas the purple arrow indicates that the sequence at Broken Hill is at relatively lower pressure. So they're the natural relations that we see. How well are these assemblage patterns in the metabasites reproduced by the modeling? Well, I won't spend as much time going over this as I did for the P-lights. Just note that there's two models. There's dataset 5 and there's dataset 6.2. And if you want to see the calculations and what they used, refer back to this slide or the papers from the original studies. But nature versus model in this green schist amphibolite transition, well, Paul's work here, this is his diagram for dataset 5 for his average metabasite that he uses from the Flin Flon sequence. And he finds that he can predict hornblende coming in before oligoclase in an area from, 3.3 to 4.4 kilobars. So that fits quite nicely there. And then the Mount Menzies sequence with the comets and volcanics, that would be at lower pressure, and it correctly predicts that you would have oligoclase before hornblende. So the order of these isograds is really, really important. We compare that to what Paul got when he ran the same calculation same chemical composition, just with different solution models and the new data set in dataset 6.2. And Flin-Flon, in order for hornblende to appear and then oligoclave to appear and then to be stable at the same time, you have to have your sequence run through this much lower pressure area here. And therefore you have to ask, well, where does the Mount Menzies fit with this? And so there are issues with perhaps the order in which the lines appear on this phase diagram here. We can do the same for the amphibolite granulite transition. Here, I'm not going to compare dataset 5 to dataset 6.2 because there isn't a dedicated metabasic melt model that exists in dataset 5. And so that comparison might be slightly unfair. But these diagrams are from Richard Palin's paper that accompanied the release of the Green 2016 solution models. And it looks quite complicated, but really all you need to know is that it's a PT diagram with a kind of schematic, simpler representation here on the right-hand side. And the garnet bearing field lies at higher pressure, and the alpha peroxine bearing field lies at lower pressure and higher temperature. And so Kappa's casing fits to go through this sequence, and Broken Hill would fit to move through this sequence into the OPX. It broadly works. I won't say much more than that. Again, as we did in the P-lights, how well are the mineral compositions reproduced by the modeling? Well, these two diagrams here look complicated, but they're amphibole compositional diagrams. And so the left-hand y-axis is XMG from 0 to 1, and the number of silicon cations per formula unit is plotted along the bottom. Now, the number of silica cations in the amphibole, they exist solely in the tetrahedral site, and so it's also a proxy for the amount of aluminium that's included in the amphibole. So the lower the value here, the more aluminium that's incorporated within the amphibole. Now, Paul's work in the top diagram, that covers the amphibolite facies at Flin-Flon, and this is some of my work from the granulite facies rocks from around the world. And the slight difference between the diagrams is that the names have been changed. Paul refers to his as magnesium-hornblende and Schermerkite. My diagram is Edenite and Pargasite. That's because amphibolite facies hornblendes compared to granulite facies hornblendes. Granulite facies hornblendes have a higher Edenite component, so more potassium, sodium in the A site compared with them. But essentially, they're the exact same diagram. So here is where Paul observes his Flin-Flon hornblende compositions to see this purple circle that I've outlined in red here. And this is where I observe the range of compositions in my granulites to be. Slightly higher XMG, perhaps a different composition, but similar in terms of the silicon content to some of Paul's amphiboles. Paul did some modeling in dataset 5 that I showed, and you can see that the silicon contents overlap quite nicely with what we predict. But if you compare that to what he found in dataset 6.2, dataset 6.2, the amphibole has much less silicon in. And that's exactly what we found in the granulite facies too. They don't match. There's no overlap between the compositional fields of the predicted hornblende or amphibole, which is with the stars here, and the hashed fields, which represent my natural observed hornblende. We found a couple of other issues here. The number of calcium cations in our hornblendes observed is typically greater than 1.8, so these hashed boxes up here. Whereas if you predict the hornblendes for the exact rock compositions in dataset 62, they have much less calcium in. They're really quite low in the number of calcium cations. And because I said Edenite components are important in amphiboles in higher grade granulite facies, you can see here that our observed potassium versus sodium cations in the A site, we get quite a lot of potassium cations in the A site and a similar number of sodium cations. And you compare this to what dataset 6.2 predicts, and it doesn't get to the high number of potassium cations that we observe, and it also over-predicts the amount of sodium that's present in the A site. So at this point, you might ask, why do I care that my amphibole isn't predicted correctly? Or thinking back to the metapelites, why does that matter? Well, the answer is that if you get the composition incorrect in the model, that has a knock-on effect for the modal abundance and the topology of your phase diagram, and thus has an effect on the pressure temperature estimate that you may make. So here are some diagrams that illustrate this quite nicely. These are ACF diagrams, aluminium, calcium, iron, and magnesium added together here as one component. And I plotted the major minerals: garnet, OPX, clinopyroxene, plagioclase up here. And then the crosses are the I suppose, ideal amphibole compositions. So this will be tremolite, pargasite, and shermacite. And you can see that my observed compositions of amphibole, they sit quite nicely along this kind of join with a constant calcium content and varying aluminium content. And this blue oval here, which is highlighted on this represents the compositions that the model calculated for each of my rocks. And you'll see that it lies at lower calcium content, it's further away from this calcium axis, and it's at higher aluminium content. So remember that I said that if you've got less silicon in the amphibole, that's overtaken, the space is taken up by aluminium. Well, it sits higher up here. And you might think, well, again, Jacob, why does that matter? Well, the point is that if your bulk composition was this one, this green diamond, it now sits closer to the clinopyroxene join and further away from the hornblende join. And that affects the modal abundances. And in turn, if you're predicting less of a hornblende that has less silicon in it, then there's lots of silicon that's available in the model for something else to take up. And so often, if you go and model amphibolite Feishi's rocks, and I found this sometimes in different data sets, you overpredict perhaps quartz or something that's where the silicon can appear. So that's why this is really important. And so that brings me around to my conclusions, and I hope I've not run too far over time here, but I'd like to make these quite clear. Number one, the choice of data set and solution models that you make affects not only the compositions, but the abundances and the assemblages that you will see. And in turn, it's going to affect the pressure temperature estimate you make, and therefore the tectonic interpretations that you make after that. And so my advice is, please go and experiment with the different data sets and solution models in your own rock, especially if you're running these in Theriac Domino or Perplex, where all it takes is to set up the calculation and push a button. Have a look and determine what's the consequence of the choice that you make. Would you get a different answer if you used a different data set or solution model? My second conclusion is that I hope I've convinced you that natural data reveal these repeated, consistent, and systematic patterns and are of incredible use to us. And so I'd like to encourage you to compare your own natural data, not only with patterns that are documented in nature by other authors, but to the predictions in different data sets, and use that to help you define which data set you're going to use in the end to do your pressure temperature modeling. And I'll end by saying that I think we're on a path towards improving data sets and solution models. There are pros and cons of using different data sets, and I can only hope that these natural data and these databases will help refine them in the future. So thank you very much for listening. If you've got any questions or comments, I'm sure there's some in the Q&A that we can ask, and yeah, I can email any, if I can't answer any and we don't get to them tomorrow or today, please just send me an email. The rest of this just has my bibliography, and if you're interested, these should all be hyperlinked so you can access them really easily. Thank you very much.
Great, thank you very much, Jacob, for this very, very, very nice overview. And I have to say that usually in a PhD, during a PhD, we look at 100 samples and then we investigate a few of them in details. But in this case, it's quite impressive to see such a large amount of data from so many samples. I mean, you were talking about more than 1,000 samples in your database. So this is quite impressive. And in fact, I will start with just mentioning the comment from Matt Cohn in the Q&A that is, oh my God, what an heroic effort. So well done, Jacob.
Thank you. I mean, I should say this is a long time coming. The Feishi series is something that Dave has been working on for a long time, and he's been compiling data behind the scenes. And it's just that we thought it was about time to kind of put this to bed and pull everything together. And yeah, it's slowly become a part of my PhD. But I shouldn't. The comment of a normal PhD, you go and analyze, and that's what I've done as well. Looked at sequences in real great detail. They're the kind of studies we need. And the hope is that this database will help inform those studies, that you can come and look at our database and say, okay, well, which sequences haven't been studied in that in depth? Which minerals haven't been analyzed? And where could we add to what doesn't exist in the nature? Because it's a hard enough time reading literature it is and trying to work out what should be done. So yeah, I should add that. All credit to Dave Patterson. Yeah.
Thank you. We have quite a lot of questions for you. Let's get started with the database of your natural data. So, for example, the ferric iron. In low-grade metapelites, let's say below 400 degrees, we commonly have a lot of carbonaceous material. And this has been largely used for Raman thermometry. So the question is your average value of XFS3 plus compatible with the presence of graphite in the rock?
Yeah, that's a really good question. So the issue with that is that in these whole rock analyses, in order to classify them, I have to know whether or not there is graphite in the rock and what the oxide assemblage is. And unfortunately, and this is kind of a plug here, that if you're doing whole rock and reporting these things, please look at your oxide assemblage and tell me what it is. Because as we know, if there's graphite in the rock, then you're at relatively more reducing conditions. However, what I would say from the small analysis of the database I have done is that many of the rocks that include, that have graphite listed as part of the assemblage, they still have 0.1, 0.15 XFE3 plus in the rock. And I think it's just an underappreciated point that, you know, you put a little bit in muscovite, a little bit in chlorite, staurolite, garnet, biotite, and it all adds up to more than we might think. How much of an effect it has on the phase relations until, you know, we know it has a large effect, because if you're simply taking your iron and oxidizing it, then you're affecting the XMG ratio, and that has massive implications for the mineral assemblages that you're developing. That small amount of iron 3 plus, I think it still stands to be reasoned with how big an effect that might have on your phase relations. Yeah, I hope that answers your question. That was a really good question about the graphite. Thank you.
Yeah, it does. Thank you. I have a follow-up on that one. Do you observe a correlation between the Tmax of the sample and the XFS3 plus if you consider all the samples of your database?
Yeah, that's a really good question. So I know that there are some older studies back in the 60s and 70s that found that XFE3 plus decreased with metamorphic grade. And so if you go and look at Jay Ague's 1991 paper, he states something about that and has, I think, 40 or 45% of the total iron is iron 3 plus in his slate, a similar number in his green schist Feishis, and then about 25% is amphibolite. I haven't gone through and done the grade classification in my whole rock database yet. That's kind of the next step. I just wanted to look at the broad variation in AFM, but you're right. This is kind of a tangent to the question, but the beauty of the database is that if you can take these 2,500 analyses and we can classify them into broad pressures and temperatures, perhaps not as good as what we have in the Metapolitic database, we can use those to define, are there distinct changes with grade? Yeah. So the answer is no. Sorry, I haven't done that yet.
That's okay. That's okay. Just a follow-up comment on that from Darrell Henry. Most of our work on biotites from graphite-bearing metapelites indicate about 12% Fe3 plus in the biotite, but magnetite-bearing metapelites are about 20 to 25% Fe3 plus. But
that's a good comment. Yeah, no, thanks very much, Darrell. So the whole point of this database is that I haven't really, it goes further than what I've shown here, right? So I've simply shown you what is the average. But what I also managed to do with this data is, because many of these older wet chemical studies are so detailed, I'm fortunate enough that they do know whether there's graphite, ilmenite, magnetite, hematite. And so I've been able to go through and classify the biotites according to which oxide phase they coexist with, and look at the amount of iron 3 plus that is predicted as a result in that. And so, yeah, Darrell's absolutely right. The work by Darby Dyer and Charlie Godotti and Darrell and others in West Central Maine, it shows that and I think that most of their work focuses, and Dal can correct me if I'm wrong here, on the graphite-bearing, ilmenite-bearing metabolic rocks, and that's where the majority of their analyses are. I think that's right because your data's in my database, so I should be saying that right. And then there are a few magnetite-bearing rocks, and then 1 or 2 hematite-bearing rocks. And so my hope with this database was to expand that to look at what is the difference between biotite coexisting with these. And within statistical uncertainty, and I don't have the slide here, unfortunately, there is an increase as you go from ilmenite to magnetite to hematite-bearing rocks in the XFE3+ of biotite and muscovite. Great,
thank you. We're going to continue on the ferric iron topic because we have a lot of questions. And the next one is more a clarification. Are the iron 3+ data, the XFE3+ data, or some of the data that you compiled, are they obtained from titration? And the point is, do you consider a bulk analysis? So do you consider all retrograde minerals and weathering in addition to the main assemblage?
Okay, so I think that's kind of, I don't know whether this, are they referring to the minerals or the whole rock? I can comment on both.
At the moment, we are looking at the whole rock.
The whole rock. Okay, cool. Right, we'll just move back to that slide then quickly. Okay, yes, no. All I have done here, I have only included whole rock data. Now that means it could be ICP-OAS, it could be XRF, or it could be wet chemical if it's from the older literature. And then I've included all data from those techniques, and I've also included any data that had an iron 2, iron 3 determined, and typically that was by titration. And so obviously there are questions about if you're doing a titration, did everything fully dissolve? Did you have incomplete dissolution? And I know that people argue that's why you should take these values as perhaps a maximum for XFE3+ in whole rock. But yeah, I hope that answers the question, Pierre. Let me know if not.
No, yeah. Now I have a question on the way you plot the different diagrams, and it's again on the database. So I'm gonna read the question, but it could be challenging. So the XMG ratio, which is the mg divided by mg plus Fe2+,
yep,
versus the XFE3+ ratio, that is Fe3+ divided by Fe total, a diagram shows a weak positive correlation. Okay, yep. That's the diagram you have shown. This means that the sample with higher Fe3+ have a lower XMG value. What would the diagram XFE3+ versus mg divided by mg plus Fe total look like?
Yeah, that's a really good question. So this diagram here is just Fe2+, as you pointed out. And so that's why I think you see this perhaps weak positive correlation. And what that's saying is that these samples up here perhaps have the same total iron, but it's just oxidized. And so you end up with, you know, an Mg number that is much, much higher. You've got much more magnesium in this. If I plot it against XMG as in iron total, that's a really good question. I haven't done that because I have the data to not do that. But I would expect that all of these points over on the right-hand side, they'd have actually, the point will be made, I think. Actually, no, I don't have that. Yeah, I mean, the distribution of them, I can't tell you what it would look like. Well, the distribution will be the same as this diagram because this is Fe total here. So you would see the distribution will be the same. So there's far fewer over on the right-hand side here. They're all kind of pulled over to the center. But the obviously height or the X value or the Y value rather would be the same as on this diagram. So yeah, you would lose all of these on the right-hand side, I would imagine.
So the correlation would disappear.
Exactly, yeah.
That perfectly answers the question. Thank you. Now, if we take one of these metapelites, I have shown a few examples yesterday. Many minerals will preserve compositional zoning, chemical zoning. And usually it can be a quite large range of chemical zoning. For example, sodium-rich white micas are especially common if you look for them, and you can really have large variations. How would zone minerals affect your interpretations?
In the whole rock?
because you make an you average, okay? You make an average. So
oh, okay. Yeah, I mean, the whole log database is just what do you get if you crush the entire thing up? I'm not looking at any small complexity. So maybe I don't understand what you're getting at there, Pierre.
Yeah, for example, when you are looking at your average composition, or the average composition of muscovite is changing your PT space. Okay.
Right. Okay. So if we're looking at something like this.
Yes, absolutely.
This? Yeah. Okay. I understand that. Yeah. Okay. So yeah, that's absolutely right. This database can't take into account these, I don't know, the reaction textures and how they occur. All we can do is scrutinize the data that we pull out of the literature. And so we've purposely not included, and at least in this analysis, any of the data that have, you know, multiple white micas with different contents in the same rock. We've just tried to go for the samples that have a single white mica composition. Now, obviously, there's some uncertainty on that. How do you know that somebody didn't miss what the sodium white mica is? I can't say that. All I can say is that the hope is that this database is big enough that we should be able to get past that and filter it out. And yeah, I hope that answers that.
Yeah, you did. A personal question on that. If you would take instead of the mean that you are taking here, if you would take the maximum value of the sodium in muscovite that you have for each PT point, would you match the model?
Yeah, that's a good question. I've not considered that, but it's easy enough to do. And I think there'll be further iterations of these diagrams where we look at not only the mean, but the range in each square and how that varies. And I'd really like to come up with a way that colors and shows this according to how many go into each box. You know, if there's only 5 in one of the boxes, that's much less statistically significant than if there's 50. And that really depends on the Feishi series that we're looking at. Feishi series 4 and 5, there's a ton of Barovian sequences and a ton of analysis. So, you know, I could have in some of the Barrow zone samples, like Garnet zone, there's probably 50 samples with biotites in. It's really impressive. But yes, I'd like to show that or weight it according to that. Okay,
thank you. Now we have a request for clarification on from your slide 17. What is a migmatite in isograde?
This curve on the right-hand diagram simply represents the wet melting curve as determined by the experiment. So at what point you would see melting in water-saturated conditions. The migmatite in isograde in the field, well, it depends. I've read the papers of these different people who define it to see how they define it, and most of them just define it based on the first appearance of, I suppose, leucocratic migmatic material within their sequence. It's definitely not as well constrained and useful as an isograde as some of the other changes in the mineral assemblages, but it's something that we may consider using, and is a reasonable boundary. So yeah, I wouldn't place any weight on that, I would say. That's a really good question.
Thanks for the clarification. Coming back to the ferric iron, okay. You showed that the average pillite has 20% XFS3 plus. Huh? So yet most of the phases in your equilibrium, not your, but in the equilibrium modeling studies of pillites treat most of the iron as Fe2 plus. So the question is, how reliable is the 20% estimate? And if it is, why has ferric iron been ignored so far?
Okay, yeah, there's several layers to that question, I suppose. I suppose the first is what we talked about before. How reliable is this this 20% estimate? And I mean, I think when you've got over 1,000 analyses, it's pretty reliable to say that there's at least some ferric iron greater than 10% in all of our metapelites. Now, as to why that's not been included in the modeling, I think you have to look at it from a historical point of view. All of this wet chemical data that I collated for the mineral compositional iron 3+, that is all from the 60s and 70s before the microprobe. and was done in a time where wet chemistry was commonplace. Since then, with the advent of the microprobe, and really people have forgotten about Fe3+, so it's not an important component in the modeling to most people, although I shouldn't say it's not an important component. It's not been included in the modeling because we haven't been able to measure it easily, and there often aren't great ways of estimating it from our probe data. In certain minerals like biotite and chlorite, we can't do that. So that's why it's not really been included up until recently. And I will stick my hand up and say, when I read Dick White's 2014 paper and their extension of this all into iron 3+, I didn't quite, I think, understand why that was occurring. But now I've gone and looked at the data, and you see how much iron 3+ is in these minerals and the effects it has. And honestly, the beauty of some of these papers written in the 60s. I would encourage you all to go and read Schinner 1960, Hounslow and Moore 1967. These really thorough studies looking at the difference between ilmenite, magnetite, and hematite bearing rocks and the difference in the iron 3+. It's a whole other category of study, in my opinion. And these are why we need to have iron 3+ included in the models. The question is whether, as they're currently incorporated, that we don't have good experimental data for the iron 3+ N members, and so they're made from other N members, as I think you showed in your talk, Pierre.
So thanks for the suggestions. I'm gonna check those papers. And so now, concerning the natural data versus the thermodynamic prediction. This is a philosophical question, Jacob. Should the natural data be used as a input data or as a test data for the thermodynamic data set and the solution model development?
I think for the moment, when we produce this database and it has all these correlations in, they should be used first as test data. Because as you pointed out in your talk, Pierre, there's still a way to go with including experimental data into the thermodynamic data sets and solution models. And so I think we should go as far as we can, perhaps with the experiments, by using some optimization strategies and trying to fit what we see. And then there are obviously going to be things that the experiments can't get at, like iron 3+, that perhaps often isn't measured in the experiments, or other values. And so I think that we need to use the experiments where we can, but eventually it may come to the point where if we have very repeated and systematic and consistent patterns, and we can make sure that there's no definitive kinetic effect there or other problems, then I don't see the issue of using natural data as input data. But I'm sure that's probably not the view of a thermodynamicist. So yeah.